Imagine that in an online store you buy a new t-shirt. The t-shirts cost €20, so through your bank account you transfer the money to the online store. You specifically wanted €20 to go to the online store and not to anyone else, since if they don't receive the money, they will not send you the t-shirt. Also, you want to wire just the €20, not less and definitely not more either. Maybe even you don't want anyone else to find out you bought a new t-shirt because you told your friends you wouldn't spend more money on clothes this month. So in this transaction between you and the online store, there's two things you want. One, it should be secret, which means that only you and the online store should know about it, and possibly your banks. And two, no one else should be able to alter the message into, for example, transferring €200 instead of 20. There are many more examples in real life where you want the message to remain either private or intact, or both. For example, when your teacher emails you your grade, which you are actually embarrassed about, or when your friend tells you a secret that no one else is supposed to know. The bottom line here is that when sending a message, in most cases in real life, we want to do so securely. In this video, we will consider the following scenario. Alice, here on the left, wants to send a secret message to Bob, on the right. Unfortunately, Alice and Bob are far away from each other and only have means to communicate that can be intercepted by an eavesdropper, usually called Eve. For example, if Alice and Bob use computers with a cable in between, then Eve could be tapping the cable. Or if Alice and Bob use regular paper mail to communicate, Eve could be the postman who consequently open and close the letters. The main question here is, how can Alice and Bob communicate such that Eve cannot read their messages? One way to solve this problem is by using a scheme that allows us to send messages securely, which is the so-called one-time pad scheme. Disclaimer, in this entire video we will not deal with any concepts from quantum computing or quantum communication, but we will use the concept explained here in the next video, which is about secure communication using quantum devices. In this video we'll do three things. First, you'll see how to encode a textual message into bits, zeros and ones. Then we will see how the one-time pad scheme for secure communication works. And third, we will note some issues with the one-time pad for practical use. First, let us translate a piece of text to a sequence of zeros and ones. Suppose we have the following secret message. The treasure lies directly next to the palm trees. For every letter, we have now made a sequence of 5 zeros and ones. For example, every letter A we encode using the sequence 0, 0, 0, 0, 0, and the letter T as 1, 0, 0, 1, 1. By using this dictionary, we can write every letter in the secret message as a block of 5 digits. And that by gluing these blocks together, we have now translated the message into just zeros and ones. We can reverse this procedure by first cutting up the sequence into blocks of 5 digits and then decoding each of the blocks using the dictionary in the reverse direction. We can take this a step further and translate the message into a black and white image. We do so by writing every 1 as a black pixel and every 0 as a white pixel, and this results in the image shown below. Now that we know how to encode a piece of text in bits or in an image, we are ready to learn how the one-time pad scheme works. The first step in the one-time pad scheme is that Alice creates a secret key, here depicted on the left as a black and white pixel image. The key should be chosen completely random in order to guarantee security of the scheme. Alice then goes to Bob, and Bob copies the secret key, for example on a piece of paper, or he stores it digitally on his computer. Now Alice and Bob go their own way each, and later on Alice wishes to send a secret message to Bob. The secret message is "Hello there," here depicted on the left of the screen as an image. In the one-time pad scheme, Alice takes her key and takes the so-called bitwise exclusive OR, or bitwise XOR of her two images. This means that for every pair of pixels, one from the message and one from the key, she creates a new pixel, which is white if the two original pixels had the same color, and black if they were different. The new image she creates this way is called the ciphertext. This is the image she will send to Bob. Bob then receives the ciphertext and is exactly the same as Alice did. He takes the pixelwise XOR of the ciphertext and the key which he had copied from Alice beforehand, and if you take the XOR of these two messages, out comes the original message. It might take a bit of thinking to understand why you get the original image back if you take the pixelwise XOR with the key twice. I encourage you to try to understand why this is the case indeed. Now, the only thing we now need to think about is Eve, who has access to all communication channels between Alice and Bob. In particular, Eve can intercept the ciphertext, but since the key that Alice used was completely random, the ciphertext also looks completely random to Eve, who does not possess the key. Using this one-time key, Alice has thus sent her message securely to Bob. You probably already guessed from the name that a one-time key may only be used once. Let us see with an example why this is the case. Suppose that Alice wants to send a second message to Bob and uses exactly the same key as she had before. She goes through the same procedure with the pixelwise XOR of the key and the message, and this produces a second ciphertext, which she also sends to Bob. Since Eve has access to all communication channels between Alice and Bob, Eve also intercepts this message. But now the situation is very different. Now Eve has two ciphertexts. And by taking the pixelwise XOR of the two ciphertexts, she gets the pixelwise XOR of the two messages, which Eve can now suddenly both read. Again, it might take some thinking where the XOR of the two ciphertexts result in the XOR of the two messages. The underlying idea here is that adding the two ciphertexts is an addition of the first message, the key, the second message, and the key again. Taking the XOR of an image with itself yields a completely white image, so we could also say that the key drops out. The result is thus the XOR of the two messages. I encourage you to try to take a piece of paper and try to work out that the XOR of two ciphertexts indeed equals the XOR of the messages. So we have seen that the one-time pad scheme can be used to send a single message in a completely secure way. You might wonder if the one-time pad is used a lot in today's world, where we use email, bank transactions, and other digital means of communication almost every day. The answer is no, because the one-time pad has a few practical issues. First, we have just seen that it may only be used once if you want security to be guaranteed. So every time you would want to send a private message to a friend, you need to establish a fresh secret key. Second, the key must be as long as the message itself. This can become impractical if you want to watch a movie online, which quickly reaches to a gigabyte of data. And then, in practice, perfect randomness is hard to produce, and maybe most importantly, how do you bring the key to the other party? You don't want to go to the physical location of your bank every time you want to transfer money online. There are several ways to overcome these problems, mostly by simply using different schemes which have disadvantages that the one-time pad scheme does not have. But there is a way we can still use the one-time pad, and that is by the use of quantum key distribution, which will be the topic of the next video. Now let us briefly summarize the contents of this video. In cryptography, we deal with the encryption and decryption of secret messages. We cannot just send the message itself, since an eavesdropper might read it, or even worse, tamper with it. We have seen the one-time pad scheme in which Alice and Bob use the XOR operation to encrypt and decrypt. And lastly, the name comes from the fact that the key may only be used once if security against the eavesdropper needs to be guaranteed.